Okay, so welcome to the session on uncertainty. Our first speaker will be Shun, presenting approximately optimal queries for planning in real uncertain Markov distributions.
Yeah. So hi, welcome to my talk. So my name is Zhang. I'm from University of Michigan. And today I'm going to present our work on approximately optimal queries for planning in reward uncertain MDPs. And this is joint work with Professor Edmund Durfee and Professor Satinder Singh. So first, let's consider a human-robot interaction problem. So suppose we have a robot that takes actions on behalf of a human and wants to maximize the human's utility. But the robot may be uncertain about the true reward function in the human's mind. So the robot may ask itself, like, what the human really wants. So there are many work like deal with this problem. For example, we can do like learning by demonstration. The human can just demonstrate the optimal behavior, and the robot can infer the true reward function given the demonstration. Or the human can always like supervise the robot and give its feedback during its execution. But this kind of work kind of assumes that we need much effort, human's effort in this training process. But in the real world, the human may not be always available, or it may not be an expert in training the robot. So in our work, we consider setting that the robot should ask the question to the human before it plans. And concretely, we assume that the robot asks a key response query and receives the human's response before it plans. And the key response query is like a multiple choice question with key possible choices. And in this toy domain, we can see that there's a red dot and a blue dot, and the robot may be uncertain about which one to pick. Well, it can only pick one of them. So you can ask, like, do you want me to pick the red one or the blue one? And this is an example of the binary response question, because there are only two possible responses. And so the key here is the parameter we provide to the robot, and the key should be small for human to easy to respond. So there are two contributions in our work, and I'll start with the first one about finding approximately optimal key response policy query. So I'll start with the formulation of our problem. So you may have seen like the standard definition of Markov decision process, and here we use a variation of it called the reward uncertain MDP. So we still have the S for state space, A for the actions, T the transition function that captures the dynamics of the domain, the environment, and S0 is the initial state. And rather than having a concrete reward function, we have a set of possible reward functions denoted by curly R, and also a prior belief about which the reward function is the true reward function, denoted as psi. So these two elements are known by the robot. And there's one reward function in the possible set of reward functions called the true reward function, denoted by R star, that's only known by the human. And this is the reward function that we are going to evaluate the robot's behavior. So just remind you that we assume that the robot asks a key response query before it plans, and also receives the human's response before it plans. So a key response query formula is just a set of key possible responses. And at this point, we make no assumption on like what kind of elements are in this set. They're just they're just generally key possible responses. And we assume that both the robot and the human knows the response model, which means how the human would respond to a query given the reward function. So use this response model, the robot can do a posterior update. That is, he can compute that what's the probability of a reward function R being the true reward function, given the prior belief psi, and also the human tells me the response J in the query queue. And then after the posterior update, the robot can just compute the optimal policy under that belief. So here's the roadmap about our first contribution, because some of them are based on the previous work. So we first start with describing the objective function, that is, what the query is optimizing. It's called expected value of information. Then I argue that there will be no loss if we only consider a specific kind of query called policy queries. And then I'll mention a describer algorithm from the literature that for one-shot decision making, not for MDPs. It's a graded construction algorithm. And then I'll modify that for our work, for our context. So first, the objective function is called the expected value of information. So although the robot doesn't know that when they ask a query, what the human would respond, but you can imagine that for all possible responses, what the ultimate posterior value would be if given that response. then it can take the expectation of those possible posterior values and compare that value to the optimal value of under the prior belief. Then that's how much the response of the query would improve my planning expectation. So now we define the key response queries and also the objective function. So can we just find the optimal query directly? Well, so at this point, we make no assumption on the forms of queries. So basically, we have an infinite space of queries as long as they have k possible responses. But we argue that we can focus on just key response policy queries. So I first define what a key response policy query is, and then I'll justify why we can do so. So a key response policy query is a set of key policies, and the human would respond with the policy that has the largest value and the true reward function. So what is this kind of query good for? Well, so suppose so we can claim that the optimal key response policy query is optimal key response query, which means that we can focus on find the optimal key response policy query, and the optimal query would be, in general, the optimal key response query. So this can be proved formally by the intuitions that suppose the Q star is the optimal query, then for each so we don't assume the form of it. It could be the arbitrary form. Then for each response, the robot can compute what I would do given this response, which gives us a key response policy query. Then it would be same to ask this policy query as ask the Q star. Okay, so did we solve this problem? If we know that we only need to consider key response policy queries, well, it's still quite expensive to find the optimal policy query directly, because considering the size of the space of just deterministic policies is already the number of actions to the number of states. Not to mention that we need to find k such policies and evaluate all of them as such subsets to find the optimal one. But fortunately, there's a method in the literature called a graded construction method, where we don't need to find the k policies altogether. Instead, we start with the first policy to add to this query. Then we fix that. Then we find the second policy to add, so that these two policies form a good two-response query. Then we fix these two policies, and we add the third one to find the good three-response policy query. And we keep doing so, and we have k elements in the set. So the good news is that we can show that the query found in this way is approximately optimal. We can have a theoretical bound. But still, we don't know how to find the next policy, because we don't want to really enumerate all the policies to find the next one to add. So here's the crux of our first contribution, is that we found the next policy to add to this set without enumerating all the policies. Okay, so I have one slide to show the illustration of our approach. So the intuition of this problem should be quite simple. It's like we already have some policies in the query. Then we want to find the next one, but then to build a good query with one more element. Then the new policy we added should naturally complement what's added to the query. It should ask something very different from the human, because the bad choice would be just add the same policy already added. Then it will elicit no new information. So here's the illustration of our procedure. So suppose we have already I-1 policies in the query, and we also plot for each reward functions what's the value of the best policy can be achieved in this query. For example, for R1, some policies achieve quite a high value, but for R2 and R3, none of the policies achieve a good value. Then what we want to do is that we want to find the next policy to add to the set, pi1, so that the region it outperforms the values obtained by previous policies is maximized, which corresponded to the shaded area in the figure on the right. So we can show that to maximize this area is corresponding to a mixed integer linear programming problem, and we can just solve this problem to find the next policy. Then I'll mention some details about this approach. So first, we can justify that maximizing the areas of this sparse is the right thing to do. It's called the expected utility of the selection of a query. So this is a concept used in the literature, and we generalize for policy queries. And then we can also show that the query that maximizes this area would be the optimal query. So here is the algorithm of our greedy construction approach. And in the third step, we find the next policy to add to the set so that the US of the union of the added policies and the new policy is maximized. So of course we can't like enumerate all policies to find the one that maximize this US. So we solve this mixed integer linear programming problem. And I'm not going to cover the details, but I want to mention that we do have an integer for each reward function in our formulation. Because recall that we only want to maximize the region you outperform some reward function compared to the values obtained by previous policies. So there's some non-linearness on what value you count. So that's why we need an integer for each reward function to track that part. Okay. Now we come to the evaluation. So we want to see that whether the quality of the query found by greedy construction is comparable to the optimal policy query. And also we expect the computation time of the greedy construction policy query should be much less than finding the optimal query directly. So the domain we evaluate on is called a rock collection domain, where we have robots that navigate in a domain to collect rocks, but it's uncertain about which rocks have rewards. So they have access to a set of reward functions, and each subset of rocks have positive rewards. So, and also we have different reward settings, but I'm going to mention that later. So now we report the results of both EVOI, which measures the quality of the query, and also the computation time. So here we report two results on the first. So in each cluster, the left one is the optimal policy query, and the right one is the greedy constructed policy query. And we can see that in terms of quality of the query, they have quite close performance on the right in the figure on the left. And on the right figure, we can see that it's very expensive to find the optimal query directly, where our greedy construction method is much more efficient than that. So here concludes our first contribution, and I'll mention about the second contribution on trajectory queries. So although that we argued we can focus on policy queries, and we have approach to find the approximately optimal policy query, but in the HRI problems, people rarely use policy queries directly because there's some downsides about this. So first, it could be very efficient to communicate a set of policies to the human and let the human to pick the best one. And also, policies are naturally quite hard to interpret than other things like trajectories. So we found what's more popular in the HRI literature is asking trajectory queries rather than policy queries. So how do we find? So first, I'll define what trajectory queries are. So a trajectory query is a set of trajectories where a trajectory is just a sequence of state action pairs that can be realizable by executing some policy. And to be consistent with the literature, we assume that all the trajectories in a trajectory query start from the same state, and also they have a finite length which is fixed, which should be much shorter than the task horizon. So you don't want the human to watch you perform the whole task. And the human would just respond with the trajectory that is most closest to what he would do. So can we do something similar, like just finding the trajectory query by also use the greedy construction approach? So unfortunately, we can't do this because the trajectory queries doesn't satisfy some conditions like in policy queries, and we could literally just repeat the greedy construction approach, but we have no optimality claim on the query finding this way. But what we could do is that we find the greedy constructed policy query first, although we can't ask the policy query, but then we find the trajectory query that is most similar to what it asked by the policy query. And by the similarity, we adopt a criterion like a conditional entropy function that compares how close two queries are. Okay, now so I'm not describing the concrete details about this algorithm, and we want to say that we want to compare this method with some competing methods with literature also found trajectory queries. So the red boxes are our method, and the blue boxes are some methods from the literature which focus on minimizing the reward uncertainty after we ask a query. So we can see that in all reward settings, our method outperforms their methods. And in one of the settings, which is number 3, we have, so in this setting, we have one reward function says there's a very large positive rewards, while others says there's a small rewards. Then the right thing to ask is whether this R1 is true or not, to try to distinguish R1 from others. And because the competing methods only focus on reducing reward uncertainty, they can't distinguish really this difference between R1 and other reward functions. So this is where our methods outperform the competing methods the most, because we have the knowledge of what the optimal query would be like. So we also evaluate a different domain, which is more realistic, called discrete driving domain. So the robot here is like an autonomous driving car, and the human may have different driving styles. And we want to elicit what's the driving style that the human has. And what we vary is the number of possible responses. You can see that mostly in all settings, our method outperforms the other methods. But when there are a large number of possible responses, then the advantage of our method decreases, because when there are more responses, then this is essentially an easier question, and you can use whatever heuristic to find a good query. And the difference between our method using the optimal querying strategy, which is not that doesn't have more advantage compared to others. So here, I'm not going to read everything in this slide, but I'll emphasize again our contributions. So first, we have a greedy construction approach to find approximately optimal policy queries, and then we have a strategy to find trajectory queries by using the information in the greedy construction policy queries. And so thanks for attention, and I'm happy to take questions. Thank you.
Yes.
Yeah.
So I guess 2 questions, and then one question. So first, would it be easy to generalize this to not a finite set of reward functions? So normally in IRL, they'll have a linear combination.
Right, so here we assume that the set of reward functions is finite.
Right.
But yes, it could be generalized to linearly decomposable reward functions. But yeah, we have tried this direction, but then it's hard to still guarantee the optimality bound. Well, maybe we can still find good queries, but we can't. The theorems don't go through for infinite space of reward functions.
And then the second question. You cited our previous work on trajectories, and I guess one of the major differences is we're using trajectory preferences to just directly rank policies. And I guess you're using them to rank reward functions. Do you see any distinct? Do you have any thoughts on the pros and cons of that? So we were trying to directly learn the policy, and you were directly learning the reward function.
Right. So if we just compare the policies directly, so because our goal is we want to still use the information in the optimal query, then to use that information to find a good trajectory query. So if we just go using policy, compare policies directly, it's hard for me to see how we can still prove the same optimality bound when we found policy queries directly. Is that what you're asking?
Oh, we can talk about it.
Oh, okay.
I have a question.
Mm-hmm.
So solving the MILP can be quite time-consuming. So I was wondering what is the amount of time spent to solve the MILP? Yes, the total solving time.
Sorry, you mean solving which part? Solving the
MILP, the mixed integral in our program. We are solving each step. So
right. So
how much time does it take compared to the?
Yes, I can show that in just a few seconds because we're still in a comparatively small domain. So as long as the number of reward functions, because we have one integer for each reward function, if that number is not too large, then we can solve it still in a decent time compared to really searching through all policy queries.
Okay. Any other question? Okay. Thanks.